In this video, I go over how to set up to solve for a one-dimensional or a multi-dimensional dynamics problem. This is the classic F equals ma or momentum principle problem. Let's get started. So here's the problem. We have this object for which we know its mass with time. We mark its location by its center of mass using the variable r. It has some velocity, variable v. It is affected by external forces as shown here in red. We know initially where the body was and what its initial velocity was, and our goal is to find the location of the object at all times with this information and how the forces change with time, space, and velocity. To do this, we apply the momentum principle. This is the principle that Newton developed, that the momentum of the object is equal to the net force on the object. Mathematically, we mean the net force as the vector sum of all external forces, for which each external force may be a function of the body's position, its momentum, and time. And we know that the momentum affects the position of the object. This is an expression that includes the fact that the object could be moving relativistically and the mass could be changing with time. However, for most of the problems we're going to be doing, since c is the speed of light and it is huge, everything essentially cancels out and we can approximate the rate of change of position as equal to the momentum divided by the mass. Therefore, the modern mechanics approach is that position changes due to momentum and momentum changes due to the net external forces. However, the traditional introductory physics approach is that we use the net force on the object is equal to its mass times its acceleration. The net force is, as before, the vector sum of all the external forces. However, this approach is actually incorrect. It makes the assumption that the mass of the body never changes, and it assumes the body never reaches a relativistic speed. Finally, it introduces an intermediate step. Position changes due to the velocity, and the velocity changes due to acceleration, but the acceleration now has to be equivalent to the net force over the mass. For this problem-solving approach, I will reduce it to the following: that the rate of change of position is due to velocity, and the rate of change of velocity is due to the net force divided by mass. Let's begin with the one-dimensional approach. First, we need the position equation, which is that the rate of change with respect to time of the position is equal to the momentum of time divided by mass. That is our approximation. Shift enter. P equation, the momentum principle, is defined as the rate of change with respect to time of the momentum, which is a function of time, which is equal to F underscore underscore net. What is F net? Well, this is where you put in all the different forces that you have on the body. In this particular example, I'm just going to make it a constant, and we'll see what the output is. Now let's put in our initial conditions. We have two rate equations, so we need two initial conditions. First one is what is x at the original time, which we'll call 0. Then we'll call it x of sub 0. Okay, comma. Shift enter. What is the initial momentum at time t equals 0? Well, we'll call that p0. And how do we want to find momentum? Well, let's just say it is equivalent to mass times velocity, where v0 is our original velocity. Now we're ready to solve. Solutions, colon equals dsolve, open parentheses, open curly bracket, because we got to list all the equations. The position equation, the momentum equation, and the initial conditions. These equations may look familiar. Let's extract it out. First, I'll extract out the position, but when I do, I'm going to expand it. So I'm going to expand where I evaluate what x of t is from our solutions. And we'll do the same thing for the momentum, but this time I'll just evaluate it. Should look closer to the equations you may have in your class, that position as a function of time is equal to its initial position plus its initial velocity times time plus essentially the force effect. What if we want to do this in 3 dimensions? Well, again, now we have a position equation, which now will be involving our position and momentum, and we have a momentum principle equation, which is our momentum and the force. We have to define what each of these vectors are. So this is something to do with x and y and z. And the same is true with momentum. Our net force is also a vector in 3 dimensions. We must include the initial conditions for these 2 rate equations, where the initial position has to be a 3-unit vector, as well as the initial momentum. It is useful to write out all the equations. Hopefully there are 4 of them. 1, 2, 3, 4. Notice all 4 are vector equations. At this point, we can solve again our position, momentum, and the initial equations. And as you can see, we end up with expressions for each of the momentum terms and each of the position terms. And I'll do the same as before. I'll extract out the solutions, but write them out in terms of the components for both position and momentum. And if we do the traditional intro physics approach, the equations look very similar. Again, we use the definition of velocity, that is our x equation, and we use the fact that velocity will change with time. We call that acceleration. That acceleration is equivalent to the net force divided by the mass. Again, two rate equations, therefore we need 2 initial conditions. For this problem, I'm going to let F net stay as a constant. We solve the 2 equations with their 2 initial conditions, and we get this result. And as before, we can extract out the solutions. And this is the way to solve the problem in 1 dimension. The only thing we're missing here is what is the expression for F net. That is where the physics comes in. If we work this problem in multiple dimensions, it's just a matter of making sure that each of the functions are functions of 3 components. That means both the position, the velocity, and the net force. But the physics is the same. The rate of change of position is called velocity, the rate of change of velocity is called acceleration, and acceleration is net force divided by mass. We, of course, have to provide our initial conditions, and our initial conditions also have to be written out in the vector format. Again, it is useful to write out the equations that we're going to solve, making sure that they're all of the same type and that there are 4 of them. Now we can use desolve on the position, velocity equation, and the initial conditions and receive 6 function solutions, which we can extract out from the solutions for which we can build expressions. Notice, though, that none of these things are functions. To make them a function, we have to include makefunc. So we make the function by saying that this is a function with respect to t. The output looks kind of ugly, but it is a vector. It is a column vector with the components written out as defined by putting in some value for t and seeing that we get a vector out of it at the location of t sub 0. So there are 2 approaches to solving these problems. One is the more complete solution, which is the modern physics approach, i.e. using the momentum principle, and the other is the traditional introductory physics approach, which is F equals ma. Both approaches allow you to solve either a 1-dimensional problem or a multidimensional problem. And with both approaches, while you try to find a closed form solution for position as a function of time, sometimes that's not possible and we have to come up with a numerical approximation. The next video will go over a series of examples, some of which I can find a closed form solutions and some of which we just have to use the numerical approximation.